Hello and welcome to the 8th and final video of the M2 chapter, Centers of Mass. On the screen, an exam question to get us going. Pause the video now if you'd like to try this before watching the solution. The opening paragraph here just tells you what you can see in figure 2 here. So we need to calculate to three significant figures the distance of the center of mass of the plate from AD. We don't need to calculate from DC. I suspect that is because you can see it is a symmetrical shape. So the center of mass must lie along this line of symmetry here, 5 centimeters from DC. So if we need that at any point, we already know it. If I put X and Y on here, what I just said there is effectively Y bar equals 5. Part A is asking us to calculate X bar. So to do this, I would do my little table. We've got relative mass, and we're going to take the big rectangle and subtract the circle, and then have our final figure. 20 times 10, 200, and here we've got a radius of 3, so that's 9 pi. 200 minus 9 pi. Then we need the x-coordinate of the center of mass of the rectangle is 10, and of the circle is 6. Here, x bar. So we've got 200 times 10 minus 9 pi times 6 must equal 200 minus 9 pi times x bar, which gives us a final answer of 10.658 ... which to three significant figures, 10.7 centimeters. Part B. The plate is freely suspended from A and hangs in equilibrium. So if we're suspending from A and the center of mass is along the line of symmetry at 10.7 centimeters, it's about here, call that G, then the vertical line must go through G from A. In an exam setting, I would be careful to put that word on your vertical line to make that really clear for your examiner. Calculate to the nearest degree the angle between AB and the vertical, this angle here. That's not so bad compared to some of the examples we've done. This is 5. The distance along the top from A to this point here is 10.7. So for part B, tan of theta is equal to 5 over 10.7. Theta is equal to 25.04 ... So to the nearest degree, 25. And there is our exam question finished. In this video, we're just going to extend these ideas a little bit to look at non-uniform composite laminars and frameworks. So all of these ideas so far can be used for non-uniform laminars and frameworks if you know the way in which they are non-uniform. So if it's just declared to be non-uniform, that's very difficult. You need to know the way in which it is non-uniform. For example, you might be given information about the masses of different sections. It might simply tell you, this part is this mass, this part over here is this mass. If you know that information, you can treat it as particles on a plane. Or the context might imply a relation between the masses of different sections. Some of the examples we'll look at will be paper or card folded over, so you know that it's a uniform laminar initially, but one part where it's folded will effectively be double the mass in that section because there's 2 layers of paper. So although you might have some non-uniform laminars, they will be non-uniform in a very specific way. So we're going to dive straight into the examples, one like this and one like this, and then we'll finish with a final exam question. The triangular framework shown is made of 3 pieces of uniform wire. Now don't let this confuse you. I've just said it's non-uniform and they're saying uniform here. What they mean is each individual piece is uniform. So AB, this wire itself is uniform, but it is not uniform as a full three-piece triangle. A to B is uniform with a mass of 4m. A to C is uniform within itself, but is very different from A to B. It's only m. So although usually we would take the length to be the relative mass, here these have the same length, but very different masses. And because of that, they have to tell you that information, otherwise you just can't do the problem. Finally, BC, which is quite a bit shorter than the other two, is 3m, much heavier than AC, not quite as heavy as AB. So I hope you can see that although it's a little bit more complicated in the scenario, it's actually a very easy question because it's just being reduced to 3 particles on a plane. We know the midpoint of this uniform rod, the midpoint of this uniform rod, the midpoint of this uniform rod, and we're being told outright the masses. We don't need to worry about relative mass. This is 4m, this is 3m, and this is m. So, as I said, effectively 3 particles on a plane. We've got 4m times the midpoint of AB, using the grid 1 square 1 unit is 1, 2, plus 3m times the midpoint of BC, 3, 3, plus m times the midpoint of AC, 2, 1, must equal the total mass of the system, 4, 7, 8m, times x bar, y bar. All of the m's cancel out. On the left, then, that gives us 15, 18, and 8 x bar, y bar. So the coordinates of the system, we've got 15 over 8 and 18 over 8. Centre of mass has coordinates 15 over 8, 9 over 4. Our second example might seem a little bit more complicated because they're not going to tell us the information like this. The context is implying a relation. So the lamina shown is made from a square piece of cardboard ABCD that has had the corner C folded over to the centre of the square. Find the position of the centre of mass of the lamina. So here we've got a uniform piece of cardboard. It doesn't actually say uniform, but it's implied here that the cardboard itself is uniform, but because this triangle has been folded over, this triangular section here has got 2 layers of cardboard. So the relative mass of this is twice the area, because it has literally got 2 areas of this triangle, one underneath and one on top. And you could even take them as separate triangles if you wanted, but seeing as they've both got the same position of the centre of mass and they've both got the same area, you might as well add them together and make 2 of them. So our approach is not going to be very different. I'm going to split this lamina into shapes that are easier to find the centres of mass of. Here we've got a square at 3, 1. Over here, a rectangle with a centre of mass at 1, 2. And here our triangle. Centre of mass of the triangle is 1/3 of the way along here. So you could do the coordinates of the corners, but I'm just going to take 1/3 of this distance and 1/3 of this distance. So this is at 2 2/3, 2 2/3. Now I draw up my table. We've got the rectangular section, the square section, the triangular section, and then the final lamina, like this. Relative mass, the rectangular section, 2 times 4, 8, and the square section, 2 times 2, 4, and the triangular section would be 2 times 2, 4 divided by 2 gives me 2, but because there are 2 layers of this, I'm going to double that to 4. Or you could put 2 times 2. The whole thing then is 16, which of course matches with the original square 4 by 4, 16. X and Y coordinates of the centre of mass, 1, 2, 3, 1, 8 over 3, 8 over 3, x bar and y bar. Forming my equation gives me 8, 1, 2, plus 4, 3, 1, plus 4, 8 over 3, 8 over 3, equals 16 x bar y bar, 92 over 3, and 92 over 3. Which I hope is not a surprise given the diagonal line of symmetry along here. The centre of mass will have x and y coordinates equal, which is what we have. And if we divide both of those by 16, we get 23 over 12. So the position of the centre of mass of the lamina is 23 over 12 centimeters from AB and 23 over 12 centimeters from AD. To finish off this video and this chapter, we'll have a final exam question based around this idea here. So it's very similar. You can see already we've got the square and it's folded over. It's not folded into the center this time though, and we need to show that the distance from AB of the center of mass of the folded lamina is 55 over 32A. So we're doing something very, very similar. I'm going to split this into two rectangles here. Center of mass for this one is here, and for this one is here. For the triangle is about here. And I'm going to go straight into a table. So we have this rectangle and the horizontal one, which is not quite as long. Then the triangular section and the full lamina here. Relative mass is 4a squared. For this one is 3a squared. And for the triangle, 3a times 3a is 9a squared divided by 2 because it's a triangle, but then multiplied by 2 because it's got a double layer of the cardboard, is 9a squared total. The mass of the whole thing, as we should expect from the original diagram, is 16a squared. We're only asked to find the distance from AB, which is what I would normally call the x-coordinate, because the x and y are going to be the same, due to the same symmetry as we had in the example down here. So the x-coordinate here is a over 2, 5a over 2, and for the triangle is 1/3 from here to here, which is the same as 1/3 from here to here, which is an a plus the a to get from here to here. So that is just 2a. Here we've got x bar, so our equation is 4a squared times a over 2 plus 3a squared times 5a over 2 plus 9a squared times 2a is equal to 16a squared times x bar. All of the a squareds cancel out, and you'll see that we are going to have an a in our final answer, which makes sense because x bar should be some fraction of a, and that gives us 55a over 2. So x bar is 55a over 32, and that matches with what we've been told in the question. Part B, the folded lamina is freely suspended from E and hangs in equilibrium. So the downward vertical will go through the center of mass of the lamina, say that's about there. And we need to find the size of the angle between ED and the downward vertical. So that's this little angle here. Call it theta. So I'll call the center of mass G and this point here H so that I can refer to them. We know HG, this little distance, is the center of mass 55 over 32A minus A. And that is 23 over 32A. And then we know EH is equal to 4A minus the center of mass on the y coordinate, which is equal to this because of the symmetry. So EH is equal to 4a minus 55 over 32a, which gives us 73 over 32a. Now theta is equal to the inverse tan of hg over EH, 23a over 32 divided by 73a over 32. The a's and the 32's cancel out, and effectively that's just the inverse tan of 23 over 73, which is 17.487 ... 17.5 degrees to 1 decimal place. And that is the final answer of the final example of the final video of the Centres of Mass chapter. Now I hope you can have a go at some of the questions in exercise 3H for non-uniform laminars, and the chapter 3 review exercise for all of the centre of mass content. And maybe I'll see you for chapter 4.